In this video, we present the use of a new computing model introduced by Rao Michelini in his book, Designing a New Class of Distributed Systems, published by Springer in 2011. This model allows to provide all the benefits derived from cloud computing without the need for virtual machines, hypervisors, and the associated management complexity. By using a parallel signaling network overlay over a network of Linux processes, each endowed with self-management, we can provide end-to-end distributed transaction management with high reliability, availability, security, and performance. According to Paul Cockshott and others, as described in this book, Computation and its Limits, the key property of a general purpose computer is that it can be used to model any physical system of which the computer itself is not a part to an arbitrary degree of accuracy. However, their logical limits arise when we try to get them to model a part of the world that includes themselves. This is because of Gödel's prohibition of self-reflection in Turing machines. The evolution of computation can be examined with respect to three dimensions. The first dimension is the system resiliency with which its reliability, availability, performance, and security can be measured. The second dimension is the scaling with the number of computing elements, and the third dimension is the efficiency with which the computing resources are utilized to effectively compute. The conventional computing originated from the von Neumann computing model and the Turing machine has provided very effective way to model physical systems and monitor them and control them, as long as the computer itself is not a part of that model, as Paul Cockshott pointed out. Now, in order to address the system resiliency and scaling and efficiency to include the computer and computing resources themselves, we have resorted to automation of various tasks involved in resource administration, such as CPU, memory, storage, network bandwidth administration. However, this has some limitations. Number one, because the self-reflection is prohibited, the layers of software that we have started developing to automate the resource administration has increased complexity with, for example, infrastructure as a service, platform as a service, software as a service. These layers all are added on top. In addition to that, there is a whole layer now that is added, which is based on the virtualizing the resources so that you can improve the resiliency. This is with the virtual machines and the hypervisor orchestration. On top of that, we have started adding application level management, and current operating systems cannot scale beyond a certain number of cores because of their design that originated from server-centric and limited narrow bandwidth origins. So what we need is a new computing model that allows to model a part of the world that includes the computers themselves. So we need to go beyond Turing computing. And in this presentation, we will attempt to present such a new computing model. The DIME computing model is implemented by a middleware library that uses conventional Linux services. The model implements fault configuration, accounting, performance, and security monitoring and control of each process based on the context and the constraints of the application being executed in that process. A signaling network overlay allows the system-wide management of a network of such Linux processes contributing to a distributed transaction. This picture shows a simple application being monitored and controlled by the FCAPS manager. The FCAPS parameters are monitored and managed by the FCAPS manager. The Linux process monitors and controls the temperature using a thermometer and a fan. The model includes therefore both the computer and the computed, and thus pushes the computational limit imposed by the Gödel's theorem on Turing machines. This picture shows the transition from a physical server network to a virtual server network to a DIME network managing a network of Linux processes. In the physical network, we have very labor intensive resource management to match the application demands when they change with business priorities, latency constraints, and workload fluctuations. You also do not have visibility and control at the application level, fault configuration, accounting, performance, and security without very labor intensive diagnosis. You of course need many interfaces to multiple resource management systems in order to provide application level management. The physical server network works well when your requirements are such that the management transaction time is much larger than the service transaction time. This picture shows the complexity introduced by the hypervisor, the virtual machines, the infrastructure as a service, and the platform as a service components. The benefit is from automation of resource management to match the application workload fluctuations, business priority changes, and latency constraint requirements. The visibility and control of the virtual machine fault configuration, accounting, performance, and security are available without labor intensive diagnosis. However, there is no visibility and control at the application level or process level, accounting, configuration, performance, and security management without labor intensive diagnosis. You also need interfaces to multiple resource management systems in virtual networks. You also need orchestration of multiple VMs, and if you have heterogeneous hypervisors, orchestration across multiple hypervisors. The virtual machine model works very well when the management transaction time is slightly greater than the service transaction time. This picture shows the simplicity that is possible with the DIME computing model, where each Linux process is now FCAPS managed. The automation of resource management to match application demands instead of virtual machine level demands. Visibility and control of application fault configuration, accounting, performance, and security without labor-intensive diagnosis. It also decouples the services management from infrastructure management. No interfaces to multiple resource management systems, since each process is managed through the local operating system, and the network is managed by network management systems. The DIME network works very well even when the management transaction time and the service transaction time are of the same order of magnitude. In addition, the DIME computing model now allows, using the signaling channel, an end-to-end service connection FCAPS management in real time.